Okay, now let's check that this composition, the sigma hat that we defined as this composition, does satisfy the two requirements, namely that it extends sigma and also extends alpha to alpha prime. Now, why does it extend sigma? Because, okay, so let's start with something in F and apply sigma hat to it. But if we start with something in F, okay, so in here, so if I start with A in F, okay, so when I take A to here, now I'm looking at the constant polynomial A, the image of the constant polynomial A in this quotient. Now applying sigma star to the constant polynomial A, well, that's the same as applying sigma to A. So here, up to here, you're now sigma of A, the image of sigma of A in this quotient. And now, well, sigma of A is an element of F prime. What you get here will be sigma of A itself. Right? This map here, how does it act on something in F prime? Well, it just acts like identity on something in F prime. So the composition would send for any A in F, would send A to sigma of A in here, as desired. So in fact, sigma hat does agree with sigma on F. Okay, that was the first requirement. How about the second requirement? Let's see what it does to alpha. Well, alpha, see, look at this map over here. So this is evaluation at alpha, right? It sends x, so the image of x in the quotient will go to alpha. Right? So the inverse, well, where does it send alpha? It will send it to the image of x in this quotient. Where does sigma star send x? It just sends x to x, right? It applies to the coefficient. So it sends x to x. So here, now you're looking at again the image of x now in this quotient. And I'm applying evaluation at alpha prime would send x, or the image of x in this quotient, to just alpha prime. Right? So the composition sends alpha to alpha prime. So, in short, it would send alpha to the image of x, again the image of x, and well, alpha prime. So both requirements are indeed satisfied. The sigma hat does satisfy the properties that we're looking for. So that takes care of existence. And now we're gonna show the uniqueness. So this is existence. This was existence. So yeah, this proof was the proof of existence. Now let's do the proof of uniqueness. Well, the proof of uniqueness is simpler. So here's the proof of uniqueness. Well, so suppose sigma hat is called maybe 1 and sigma hat 2 from F alpha to K prime extend sigma, and both send alpha to alpha prime. I'll show that sigma at 1 and sigma at 2 are the same. The key thing is that, look, F adjoint alpha as a vector space is generated by powers of alpha. That's the point. So one alpha squared, so on and so forth, spans F adjoint alpha over F. In fact, you don't have to include all powers of alpha. Remember, this is going to be, because alpha is an algebraic element. You have to you can stop at alpha to the power of 1 less than the degree of the extension, 1 less than the degree of the minimal polynomial. So now, okay, so now what's, so every element of this field is an F linear combination of these guys. So we're going to look at sigma hat 1 of sigma of sum of AI alpha I. Well, this is now equal to, okay, so this is now sum sigma hat AI, sigma hat 1, sorry, sigma hat now 1 of alpha to the power of I, but now this is equal to, okay, remember sigma hat 1 and also sigma hat 2, they both extend sigma. Sigma hat 1 at AI is the same as sigma hat 2 at AI. It's just sigma of AI. This is sum sigma hat 2 of AI. And then, well, sigma hat 1 at alpha is just alpha prime. And, well, so is sigma hat 2 at alpha. Right, again, because both of these guys are just at alpha prime, right? And then these two are the same because sigma hat 1, sigma hat 2 are both extensions of sigma. So both of these and AI are in F. So both of these are just sigma of AI. So these two are the same. So you see that sigma hat 1 is the same as sigma hat 2 on this linear combination. Okay, so that takes care of the proof of uniqueness as well. So let's summarize what we proved. Okay, make sure that I didn't lose the camera. Okay, so what did we prove? So this was our picture, right? And we have a field we have a homomorphism from F to F prime, sigma, and we've got alpha, an algebraic element over F, a root of polynomial F with coefficients in F, and well, K prime is some field that contains F prime, and we were interested in extension sigma hat of F. The first thing we proved was that given any extension sigma hat of sigma, sigma hat of alpha is going to be a root of sigma star F. Next thing we proved was that if we assume that F is irreducible, this hypothesis is crucial here. Suppose F is irreducible, so up to multiplication by unit, it's the minimal polynomial of alpha now. Then, for any root alpha prime of sigma star F, there's going to be a unique homomorphism sigma hat from F adjoint alpha to K prime, which extends sigma and sends alpha to alpha prime.